we complete, most of the people arrive after 9 and the talks start earlier. So this is the experimental data. We take data tomorrow also. So some other information. So yesterday you were signing the afternoon list, and then the afternoon list disappeared. Just, I would like to know if someone, just by mistake, put in the bag, somewhere. If you have it, please give it back. And otherwise, we need to print another one, but it's missing, so we would like to have the presence list of yesterday. So look at your stuff. And then diff was living here, so I can change diff for the list if you want. Then here it is the list for today. Today will be available until the end, but tomorrow I will put at 9 and I will keep out at 10, so, or at 8:30, and I will keep it out at 9. So then sign this. We will keep it here just to avoid to be lost again. You come here, there's this, and you sign when you are leaving the room, okay? So let's continue with Pedro. Thank you.
All right, cool. So if I remember correctly, we stopped at matter effects. So here's what I'm going to do today. I'm going to talk about solar neutrinos to start with so that we keep the momentum on matter effects. And then I'll give you a broad overview of how to produce neutrinos, detect neutrinos, and what do we learn of it. I'm not going to go into the gore details of detection. You're going to have a talk next week, a set of lectures next week for that. So as we discussed, the resonance condition is this. The mass splitting cosine of mixing angle should be about twice times the energy times the potential, the matter potential. And let's see what happens for solar neutrinos, okay? For solar neutrinos, this term, 2eV, is the energy of solar neutrinos, let's say, is about an MeV. So let's write this as the following. 10 to the 6, this electron volts, E over MeV. So this is a little trick that I don't need to, I can keep the energy here, but I'm adding ones on my equation, so it's just a little bit more clear what is happening there. And then, if you remember, we got our matter potential as 8 times 10 to the minus 14 for an electron density of about Avogadro number per centimeter cube, okay? Let's put 100 here, so that this is more like the sun's density. This guy is actually bad. Let me get another one. For the sun's density, so let me put 10 to the minus 12, and then we have NE, 100 Avogadro number per centimeter cube. And if you just multiply this stuff, you get 1.6 10 to the minus 5 energy in MeV, density in, I think there was an EV here, in 100 Avogadro per centimeter cube, EV square. All right? So keep this number. Now let's calculate the other side. So for solar neutrinos, the other side is delta m square 2, cosine of theta 2 theta 1, 2, which is about 7 10 to the minus 5 EV square for this guy. And this thing, theta 1, 2 is about 30 degrees. So that's cosine of 60, which, if I remember correctly, is a half. So that gives you 3.5 10 to the minus 5 EV square. So what does that mean? That means that this side of the equation for one MeV neutrino is almost at that side. If the potential is larger than this, we start to beat the usual oscillations, okay? One can be a little bit more careful with this stuff, but But that's fine. The resonance condition then is met for about essentially 1 MeV or so, okay, maybe 2 MeV. So what happens in practice? Below the resonance energy, so let's call the energy where these two things are the same, let's put a little r here for resonance, maybe res. Below ERES, so below ERES, this part gets subdominant, which means that normal oscillations are dominant. So below ERES, solar neutrinos essentially feel that they are in vacuum, okay? So below ERES, we have vacuum oscillation, or well below ERES. The transition region, you gotta calculate stuff properly. And what happens here is this. So, I don't know if you know how the sun produces neutrinos. Do you know how the sun produces neutrinos? Nuclear reaction, nuclear. I'm really, no, I said nuclear. This is like a Midwestern thing. Oh God, who am I becoming? Nuclear reactions. So usually in the sun, the way the sun produces heat is by all these fusion reactions, right? And there are cycles, what we call cycles, or some chain reactions, where at several steps of these reactions you will produce neutrinos. For example, let me give you one of those, the small one, because the big one is too big for me to do here. You start with carbon-12. And then you absorb a proton and emit a photon. I think that's it. Oh, I don't have space here. Carbon-12. You absorb a proton, emit a photon. It becomes nitrogen-13. You absorb a beta. It becomes carbon-13. I guess we emit a beta, right? You emit a proton, no? And then you absorb this, that, you go to nitrogen, 14, and then it goes, right? There is oxygen here, there is nitrogen here. So as things are happening here, when you say absorb a proton, you typically emit, say, electron in an electron neutrino. So in several steps of this cycle, you are emitting electron neutrinos. In fact, the sun only emits electron neutrinos as far as we know. So as you produce this stuff, there is a flux of neutrinos emitted in the sun. This is flux, which kind of goes like this, and well, I'll do my best. There is a flux called PP. There is CNO. There is boronate. There is a line here, which is beryllium-7. I think there is another line here, which is beryllium-7. I think this line may be to the right, but fine. Yeah, sorry. So let me take this out. I think it's like this. So the end point of the PP flux, PP is from another reaction, is like 400 kV-ish. Boronate is like few, maybe 10 MeV, the end point. Beryllium-7 is like 750 kV or so, I guess. Oh, that's a great question. So, okay, let me go back to your question in a second, okay? So we have solar models, which tells you how these reactions happen. And maybe this is 850, right? You should check this number. That's exercise number 9. So we have a solar model, which tells us the cycles inside the sun, the reactions inside the sun. there are several of these reactions. There is another one which generates these PP neutrinos. PP stands for proton-proton. So just to give you a flavor, PP means that you have a proton and a proton, which goes to deuteron plus this, right? So the PP neutrinos come from this kind of reaction. And these are one of the many in the sun. But the point is, these reactions generate neutrinos at the keV to meV energies. And the low energy neutrinos, like the PP neutrinos, they feel like they are in vacuum because their energy is very small. So the matter effects are not very relevant. In vacuum, when you produce an electron neutrino and you want to detect at the Earth an electron neutrino, here's what happens, right? You produce an electron neutrino in the sun. You let this guy propagate a lot. It will evolve to an incoherent sum of nu1, 2, and 3, just because it's propagating like, I don't know, lots of kilometers. And then this nu1, 2, and 3 should be detected as, for example, nu-e in the Earth. So the way you calculate this probability is actually very simple. Is the probability of a nu-e becoming a nu-I times the probability of a nu-I reacting in your detector as a nu-e. And you sum over all over all i's here, right? So this is just, so how much nu-I there is in a nu-e? Well, UEI squared. And how much nu-e there is in a nu-I? Well, UEI squared. So if you just No. Wait. They do not have well-defined mass, so they're not particles.
Okay, so if they don't have an Young-state mass, how can I measure it?
When neutrinos interact via weak interactions, they always produce a lepton. Well, via the W, they always produce a charged lepton.
Okay.
Nu-e is the combination that produces an electron or a positron. A nu-mu is the combination that produces a muon or an anti-mu, and then so on and so forth.
So it's a combination of nu-I, nu1, nu2 that you produce the electron.
Yes, so a
nice.
nu-e is exactly this combination. And whenever it interacts via weak interactions, via charged core interactions, it will necessarily produce an electron or a positron.
Okay, now it's clear. We could change these names, right? I mean,
No. We will never change names.
Okay.
One can never change names. Like after the community agreed, that's it.
Okay.
It's like trying to change the language. It's
So
like, no.
You don't like revolutions, okay.
No. So, all right, so this is summing I of UEI to the 4, okay? So now what is that? And I probably need to see what that is. Maybe I can remember. So the PMNS matrix is something like this: C12, C13, C13, S12, S13, exponential of minus I delta. And then there's stuff here which doesn't matter for now. I think this is, if you want, C13, S23, or maybe C23. And then C13, S23. You should check. And the stuff here is a little bit more involved, but it doesn't matter for us right now. Point is, when I sum this up, this will be this guy to the 4th, C12, C13, this guy to the 4th, this guy modulus to the 4th, and you can work the trigonometrics of that and get to the following. Where is that? All right, you can work that out, and you can get to this. 1 minus half of sine square 2 theta 1, 3 minus half of C13 to the 4 sine square 2 theta 1, 2, which numerically, according to what we have measured from experiments, is about 0.55. So let's take a second there. What does that mean? That means that I produce a NUI in the sun, and the probability for remaining a NUI is about 55%. If you remember the little two-state system calculation, the oscillation probability typically went like some sine square of some mixed angle and sine square, some delta n square L over 40. A sine square of a phase will average out to a half. And the maximum mixed angle is about 1, right? So let's put a 1 here. This is the disappearance probability. So this is never larger than half. So the probability should always be between 1 and half when it's averaged out. And this is what you're seeing here. Well, that's all fine. Neutrinos oscillate, it's mirrored away. Okay. But it's kind of interesting to see what happens for the high energy neutrinos. So for the high energy neutrinos, for energy well above this resonant energy, matter effects are dominating. And that is actually very, very different. So I don't know if you remember, if you wrote down the expression for the mixing angle that I had on matter yesterday. But for very, very large matter effects, this mixing angle goes to 90 degrees. Remember, there was a tangent. The tangent goes like to, what, 0, I guess? Is it 0? For 90 degrees? Maybe. -1. It goes to -1. Yeah, sorry. The tangent 2 theta 180. So theta is 90. So the point is, at very high energy, because the mixing angle in matter, so let me do E much larger than the resonant energy, because the mixing angle in matter goes to 90 degrees, it means that when I produce a NUI, this is approximately a nu2 in matter, right? So NUI is cosine theta nu1 in matter plus sine theta nu2 in matter. Sine is 90 degrees, cosine is 0, so this is what you have. Now, there is something interesting that happens, that because the neutrinos oscillate way faster than the matter potential changes, that is, you can write a adiabaticity condition, which is this. So this is the adiabaticity condition, which tells you that the variation of the matter potential as the neutrino propagates, so this is the position of the neutrino, it's much, 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 much smaller, so the matter potential is very much slower than what drives oscillations, all right? So if that happens, imagine that you have a matter potential and neutrinos are oscillating super fast. If the matter potential changes slightly, the neutrinos can actually adapt to that change. You can be a little bit more precise, and you can just show that in terms of a differential equation, or you can open up Landau and look at two-level systems. But in fact, the system of two levels where you're changing the voltage or the potential of the system very slowly, the system remains on the same level it was when it was created. This is a known thing, which means that the neutrinos, the electron neutrinos, they are nu2 in matter, and they remain being nu2 in matter even as the matter potential goes away. So as you exit the sun, when you have no matter potential at all, these neutrinos are nu2, right? So that is actually very, very interesting, because these neutrinos exit the sun as nu2. So now, what is the probability of detecting an electron neutrino from these high-energy neutrinos? the probability is for the high energy, let me write high, it's just this, right? You want to project on a nu E, and they exit the sun as a nu 2. And this is UE2 square, which is, it's approximate, but this is C12, C13, S12 square. And that is about 0.3, okay? So let's brief a little bit. This cannot be explained by this kind of stuff. If this averages out to a half, you get a probability that is at least 0.5 for maximal mixing angle. Here, you're getting a probability below half, which means that solar neutrinos cannot be explained by just an averaged out oscillation. It needs to have matter effects. So you need to understand how matter effects affect solar neutrinos to be able to explain this. In the end, if you look at the neutrino energy and the oscillation probability, it goes like the following. So up here is your, where is that? Over here, this expression is the 0.55. Down here is that guy, 0.3. And you have something that goes like this, where this is above the MeV, this is below the MeV. And we have indeed measured this oscillation probability. We have measured very low PP neutrinos, consistent with that at the Boraxino experiment. We have measured beryllium-7 neutrinos. This guy's the monochromatic line here. We have some measurement of CNO neutrinos with a big error bar. This is very, very hard to measure. It's hard because the only experiment that can do that, so the flux is not great. The only experiment that can do that is Boraxino, but there is a background that is right there where you want to measure this. So this is essentially the generator with a background, and experimental physics is what it is. If you have a background where you want to have your signal, that's hard life. But this is super interesting for other reasons. There is, so the way you measure that, all right, so let me just put a few more data points here. These are from Super K, from bottom 8. And we can kind of see how this goes. There's a little bit of tension here, but it's not super significant. So how do you measure that? So the way you measure these neutrinos is that these neutrinos are very low energy, so it's kind of hard to measure its scattering on nucleus. So you measure them by scattering on electrons. So what you do is the neutrino comes, there's an electron from your detector, you hit this electron, and the neutrino goes away. Back to your question, how do you know that this is a solar neutrino? Well, you know where the sun is. So because this is, let's take the high energy guys here. This is 10 MeV. This is half an MeV. The whole system is boosted. So these electrons, you don't see this guy, right? But these electrons will come roughly from the direction of the sun. So at Super K, you can see stuff like this, cosine of the angle of the electron with respect to the sun distance, to the sun direction. It goes like this, where this is background. So background comes from everywhere. Signal comes from the sun. So this is how you know that these guys come from the sun. For this stuff, it's actually harder because I told you that PP neutrinos, the end point is at 400 keV. If you hit an electron which is half an MeV, this electron goes like anywhere. So what you need to have is a detector that is as background free as possible. So in Boraxino was probably, I may be wrong, but I don't think I am, it was probably the most clean neutrino experiment, neutrino oscillation experiment ever done. The backgrounds in Boraxino are just stupidly small. And what they measure is the electron spectrum, so the energy of the electrons, and a rate. And you can calculate, if you take the PP neutrino flux, you can calculate what is the rate here. If you take beryllium-7, if you take boron-8, and then there is CNO. CNO neutrinos have a, maybe I should do like this, actually. CNO neutrinos have a fairly low flux, but they should be visible. You should have data points going on here. But you have background, right? Like, for example, what can emit electrons in a detector? Any radioactive crap. So there is one specific background from the 210 bismuth. I'm just a theorist. Don't ask me more than that. That the shape of this thing, maybe this is a little bit more like this. The shape of this thing is like super similar to CNO. So this guy here would be the 210 bismuth. Because it's very similar, it's approximately degenerate, which makes measuring these guys very, very, very hard. Recently, just recently, Boraxino measured them. Boraxino has been running since when? 98, maybe? So after like 25 years of running, they finally said, oh, we see that at 5 sigma. 5 sigma from 0, right? So you have like a 20% error bar, still pretty big. The relevance of these guys, do I have time? I have time. The relevance of measuring CNO is to understand the metallicity of the sun. So the other fluxes, they come from lighter elements. So like proton-proton, then forming helium and doing something, then forming whatever comes after helium and eventually beryllium, etc. These are all light stuff. CNO comes from stuff like this. Carbon, nitrogen, oxygen, etc. These are all heavier elements, and there is a non-trivial correlation of the heavier elements and metals inside the sun, and in general, the metallicity of the core of stars. This is actually something that we do not understand very well. There are solar models which disagree on the amount of metallicity on stars, and measuring the CNO flux is one way of actually pinning that down. So it's very important for stellar physics. So good, this is all I had to say about solar neutrinos. Any questions about solar? All right, if not, we can keep pushing. So let me tell you about other ways to measure neutrinos, and this will be a bit schematic, but I'll try to focus on whatever is important. So there are other ways to measure neutrinos. One more thing about solar neutrinos. Solar neutrinos are sensitive, as we had here, where's that? To the, well, so-called solar parameters for obvious reasons. Theta 1, 2, and delta m squared 2, 1. So keep that in mind. Theta 1, 2, delta m squared 2, 1, that's solar neutrinos. There is one more thing which is important, that the resonance condition only happens for a specific sign of delta m squared. And because we see the matter effects the way we see it, we know that this splitting is positive. So the hierarchy between nu1 and nu2, solar neutrinos give us that, right? We're done. The hierarchy between nu3 and the other ones, that we still don't know. That's still an open question. So other ways to study solar neutrinos. So here's the thing. Even if you sleep for the next 25 minutes,
Okay. The experiment of solar neutrino, they take account the matter effects when try to get the value of that parameters?
Yes. Yes.
Okay.
Yes. Without matter effects, you cannot explain having only 1/3 of noise.
Okay.
If it's just oscillations, at most you have half the noise. So the only way you can go down to 1/3 is if you have matter effects, or if your delta M square was so big, well, so small, at the 10 to minus 10 electron volt square, such that the neutrino oscillations would literally take Earth-Sun distance to oscillate. And then you start with, where's that? Do I still have it here? This doesn't average out. This sine square can be close to 1. Okay. And then you can get a probability even at 0, right?
Okay.
But that would require a delta M square that gives you oscillations at Earth-Sun distances. In the dinosaur era, that was still possible. It was a possibility. Nowadays, it's dead. It's dead. Nobody talks about that anymore. We're good to go.
Okay, so for example, in IceCube, that they don't take account the matter effects because it's a small.
Well, so wait. So IceCube does take account the matter effects. It's just that they're not sensitive enough to them.
Yeah.
So they are doing their job properly, but
Okay.
the experiment is not sensitive enough to say, you know, we establish at 10 sigma the existence of matter effects. They just can't say that.
Okay.
But yeah, the reason why it's small at IceCube, the matter effects are small at IceCube, is because if you do this equation for IceCube, now you need to change this delta M square to the atmospheric splitting. This becomes theta 1,3, so it's approximately 1. And the other part of the equation, the energy, goes to a few GeV.
Okay. Okay.
So there is a resonance there. It's just hard to see.
Okay. Thank you.
Any more questions?
It wasn't clear to me the bismuth, if it comes from the star you are measuring or from your detector.
Oh, no, that's the detector. That's the crap in the detector. So the detector has a lot of stuff like calcium-40, bismuth-210.
Because you said knowing the CNO tells me about the metallicity of the star.
Yes.
How does that work?
So the deal is that if in the core of the star you have heavier elements, you should have a higher density of this stuff, which should give you a larger flux of CNO neutrinos.
So it should be more different from the bismuth that you
have
the
so
detector.
essentially, you could say that low metallicity would give you maybe, so let me erase this line. Low metallicity CNO would give you something like this maybe, and high metallicity CNO maybe something like that. So by measuring the rate itself, you can say this is more consistent with low metallicity or high metallicity.
Okay, thank you.
It's a good exercise.
So for the probability plot, how much does it depend on the uncertainty on the matter density of the sun? Because the region where the resonance happens is exactly where, like...
Yeah, so low metallicity and high metallicity would give you something like from this to that. So the uncertainty is essentially in this region. It's the transition region that is a bit more uncertain, right? If you, in some sense, if you raise the density of the sun, it's 2 eV. If you raise the energy, if you raise the density, raise the potential, you should lower the energy, so this goes to the left, or this goes to the right if you do the opposite. It is well within error bars, although now the CNO data point does give you, I think it's like a 2 sigma preference for high metallicity maybe. But, you know, 2 sigma can change. And Boraxino is kind of done, right? So I don't think anybody else will measure CNO neutrinos in the nearby future. Like Dune may be able to measure this pretty well, actually, and Hyper-K. And I think that's it. Yeah, maybe Juno can do something about these high energy guys, but the low energy guys are very hard, very, very hard.
I think there's a proposal like for using those directionality dark matter detectors when they start getting through the neutrino fog, that they might be able to get some bit of this, you know.
So the idea there is, so maybe, I don't know if I'll have time on this lecture, but I'll calculate for you the coherent neutrino nucleus scattering cross-section. But the idea is that in dark matter direct detection experiments, there is one background which is kind of hard to avoid, which is the background from solar neutrinos. Solar neutrinos come, so, all right, this is a little bit of a parenthesis. In dark matter detectors, let's take one. Let's take xenon and whatever ton, I don't care. So the way these detectors work is that there is liquid xenon here, there is gas xenon up here, and you have a dark matter coming. You know, dark matter is on the halo, we are moving around the halo, so in our frame, there is a wind of dark matter coming at us all the time. So this wind comes, hopefully hits a nucleus. You have a nucleus of xenon. When you hit it, you move the nucleus away from the electrons and all that, so there is light emission. So there is a light emission here, bam. We call this S1 for signal number 1. And then these electrons drift up. When they get to the gas xenon, then recombine, they emit light again, giving your S2 signal. And by the combination of S1 and S2 light, the relative height and the time distance between these two things, you can say this looks like dark matter. So this is all good, but a neutrino could come and do the same, exactly the same, a solar neutrino. And if that happens, it's actually very, very, very hard to distinguish from dark matter signal. One of the possibilities which has not been proven yet, like nobody managed to build a big enough detector to do that, is to detect where this nucleus has recoiled, in which direction. So in very low energy recoils, when a neutrino comes and hits a big nucleus, the nucleus comes out perpendicular to the neutrino direction. You can just calculate that. And because of that, if the sun is over there, and your event has a nucleus like, bam, in this direction, you say, well, this is actually full of background. So maybe I should look at events where the nucleus is recoiling like in the direction of the sun, so that solar neutrinos cannot do that. It is a possibility. If you do that, you actually can use your background to study solar neutrinos. It's hard. It's freaking hard. And you have atmospherics, yes. Yes. So, in principle, yes. As a theorist, yes. As an experimentalist, not yet.
There's a paper using the Cygnus design. Sorry. There's a recent paper using the Cygnus design for the directionality.
Yeah, but
they
I mean,
they do estimative based on the detector parameters. It means very, very.
It is a good idea. It is a good idea.
Hard
Don't get me wrong, but it's very easy for theorists like myself to say, oh, we can do that. Wow, I'm super excited, let's do it. And then you get to experimentalists like Carl and say, can we do that? And Carl say, what kind of background do you need? Background rate. They say, oh, 1 event per year. And it's like, yeah, we can't do it. So experimentally, life is hard, right? And up to some extent, you only know what's going to happen after you build the damn thing and start measuring stuff. So before that is a promise. Some promises are backed up very well. Some others are not, right? There are many, many examples of experiments which, when they were turned on, they had way more backgrounds than predicted, like, for example, Minibone, which has a 5 sigma anomaly. Bigger backgrounds than they predicted, but could be an anomaly. Mateus will talk more about that, I think. So I'll leave the hot potato for him. All right, so any further questions on this? Yeah, sorry for the parentheses on dark matter. So the other thing the other way to detect neutrinos, which I need to say, is beam neutrinos. So how do we do that? So beam neutrinos from a theory point of view, and you're going to learn more from an experimental point of view, but from a simplified theory point of view is this. You shoot protons in a target. A target is just a piece of metal. It's a fancy one, but it's a piece of metal. you produce a lot of crap, and crap is essentially pions and kaons, right? So pions like to decay to muon and muon neutrinos, same as kaons, but experimentalists typically can be like smarter than theorists when it comes to this kind of stuff. There is some stuff they put here with a B field. These are called magnetic horns. It's designed in a hyperbolic way, super fancy, such that you focus, let's say, pi pluses and k pluses, and you defocus the minuses. You defocus pi minus, k minus. So now you have a pion-kaon beam with mostly positive guys. This guy is then going to a decay pipe, which is essentially an empty pipe, where they decay to what they like to decay. Like, you don't control the decay, but you know the decay. So for example, pi pluses decay to mu neutrinos. And then after that, you have stuff. Like, there is something called an absorber to do something, maybe absorb whatever you produce here. And then there's a bunch of dirt that these muons, you really don't want these muons. Muons are a pain. So you just put a lot of dirt, you leave a lot of dirt there so that the muons will eventually stop. And afterwards, the only thing that survives are neutrinos. So you get a neutrino beam by hitting protons on the target. Now, why do you do that? Just think about it. Neutrinos only interact via weak interactions. They're pretty small. You do not want to produce neutrinos via weak interactions most of the time, unless it's the only way you can do it. Here, you're producing neutrinos via strong interaction in some sense. You produce these guys, the neutrino, let's say, mothers, and then they will decay. As long as you allow them to decay, what sets the production is the strong interaction, not the weak interaction. So you're gaining a lot here. Then what you do is that after your beam, you put a detector close by. Remember, Dalton square, L over E. If L is small, there are no oscillations. And you put the detector very far away, the near detector and the far detector. Of course, when you put the detector far away, like the NOVA experiment has a detector 800 kilometers away from the beam target, you got to have a big detector because flux goes like 1 over distance square. So usually the near detectors, you can live with like several tons, maybe 100 ton scale, maybe 1,000 ton at most, but you don't need more than that. You get lots of events. Far detector, if you have 1 ton, is 0. If you have 1,000 tons, it's still kind of 0. You really want to go to like at least 10 kilotons, 40 kilotons, 200 kilotons, and you know, just keep increasing the number if you can. So the nice thing about this is that you kind of know, up to some good extent, your composition of the neutrino flux, because you know that pions, for example, and you can check PDG if you want, pions will decay to this, like 99 point blah % of the time, and they will only do this at about maybe 0.5%-ish of the time. You should check this number. So you know that pions really do not decay much to nuis. Kaons do decay a bit to nuis. Kaons can have this kind of decay where you have a pi plus, a E plus, and a nui. And this is, I don't remember. Does anybody remember how big this is? Is it 10%? 20%? X%? X%, where X is different from 0. So you should check that, exercise number 10. So you kind of know where your nui and nui bar and numu and numu bar fluxes come from. There are uncertainties, of course, on the flux prediction. And these uncertainties essentially come from the fact that you're producing neutrinos via the strong interactions. So the rate of production of pions and kaons, it's actually not super duper well known, right? They will have about 10%, order 10% uncertainties. At NOVA, for example, the energy of the beam is 120 GeV. So NOVA probes atmospheric parameters. And at the short baseline neutrino experiments at Fermilab, you have a much lower energy beam of 8 GeV, but that's roughly the ballpark that we're looking at. Oh, that decay has 0, actually. Now it's good. Thank you. Thank you. Yes. Yes. Always check for charge conservation.
Of the neutrino, because it's the air, so they have the near detector and the far detector, but we have neutrino coming from anywhere.
Excellent.
Everywhere.
Excellent question. So how do you know that you're actually detecting neutrinos from a beam, right? I mean, there is solar neutrinos, there is atmospheric neutrinos, supernova neutrinos even. So the way that you know that you're detecting from a beam is that these beams, you control them very, very well. So the beam works like this. You do not shoot protons continuously in a target. You accelerate protons in a bunch, which gives the beam a very distinct time structure. Okay. So you essentially have a window of beam on, beam off, beam on, beam off. So you trigger on beam on, knowing that that is beam on, and you collect data on beam off just to see what happens when the beam is not on. So when you collect on beam off, you know the background, and you use that to infer the background when the beam is turned on. Okay. So that's how you remove the backgrounds.
Oh, okay.
Yeah.
Okay. Thank you.
5%. Very good. So 10 times larger than this guy. That's actually one of the dominant NUI production modes in beam neutrinos. Now, here comes a complication. Here comes a complication. What do you mean, off the beam axis? Well, okay, so here's the deal. So it's a little bit more into the gory details, but when you shoot protons on a target, you produce all these pions, which are focused. Of course, even if they are perfectly focused, they will decay to neutrinos, will have some angular aperture. If you look at the neutrino flux coming out of that, it typically looks like something like this. Some big blob of neutrinos, very wide. Experimentally, reconstructing the neutrino energy is a real pain. It's actually one of the main problems of neutrino physics. And sometimes you want to give more power to the beam, more energy, but you want lower energy neutrinos, like around here, for example. So what you can do is that you look not exactly in the direction of the beam, but you look a little bit off the beam axis. And what happens is this. If I have a high energy pion, most likely it's very boosted. It will decay to neutrinos in the forward direction. High energy neutrinos come from high energy pion, they are in the forward direction. If I have a low energy pion, it will decay to neutrinos not on the forward direction. So as you go off the beam axis, your flux does something like this. It goes to lower energy and gets more peaked. And experimentally, it can be advantageous to do an experiment here instead of there. Even if you have more neutrinos here you know the neutrino energy a priori way better, right? So the reason why you go off the beam axis is an experimental reason. It's just to make sure that you can optimize your experiment. But there is no intrinsic reason for that. It's essentially, can you do better when you talk about statistics and systematic uncertainties if you go on axis or off axis? If it's off axis, let's go off axis. That's it. Yes, yes, yes. So K plus also does that, right? K plus also does this at like 60% of the time or so. You cannot distinguish them. Nope, you can't. You just see a big neutrino flux. Usually, if I put the flux in a log scale, the flux goes like this, the nu-mu flux. And usually there is a peak from pions, neutrinos coming from decay of pions, and a tail of neutrinos coming from decay of kaons. But you cannot distinguish them. Like, you kind of know them statistically because high energy comes from kaons, low energy from pions, up to some extent. But event by event, you just don't know. Sorry, you do produce less kaons than pions because if you remember, a pion is 140 MeV in mass. A kaon is about 500 MeV in mass, maybe 490 and 3, and maybe this is 39-ish. So let's take this case of the 8 GeV beam. If you have an 8 GeV proton, it's actually very hard to produce a 500 MeV particle, right? When the proton hits a proton, you have partons inside. They carry a fraction of the momentum of the beam. You need enough of this fraction to produce 500 MeV particle. Besides, a kaon has a strange quark, and a proton does not have a strange quark as a valence quark. You need to create a pair of SS bar from, like, extract a pair of that from the proton to create a kaon, and this also costs you. So the number of kaon, like, I don't know the number from the top of my head, but I think for every kaon you produce, you might have, at the 8 GeV beam, about like 20 pions. At the 120 GeV beam, maybe like 5 to 10 pions. Should check this number, but it's ballpark. Any further questions before I talk about the difficulties? So this is a common thing of neutrino physics. Every time you get excited about something, difficulties comes about, but that's fine. We like challenges. So here's the difficulty of beam neutrinos, and it's actually a big one. So the sweet spot for beam neutrinos is this. The neutrino energy should be between half an MeV and 5 GeV. Not more, not less, in general. And you can say, why is that? There are two reasons. One reason for this number, one reason for that number. So for this number, it's very simple. You have a beam of mu neutrinos, which means that you really would like to be able to create muons so that you can tag the mu neutrinos. But the muon mass is 105 MeV, right? Which means that if I shoot a neutrino in a target, for me to produce a muon, I need at least about 100 MeV neutrino energy, a little bit more than that. But then the cross-section takes forever to grow. So even if you are at 200 MeV, the cross-section for producing a muon neutrino is still pretty low. So you need to be maybe about above 300 MeV. Oh, what is this? 300 MeV, okay? You definitely want to go at 300 MeV or above so that you can create muons easily with your neutrinos. So that sets the lower bound. Now, the higher bound, if you look at this, which is the thing that drives oscillations, this is for mass in delta m squared in electron volts, this in kilometer, and energy in GeV. Let's see what's the highest energy we can go so that we can actually do oscillation of atmospheric neutrinos. So the delta m squared for it, let's take that this is about 1, okay? And I'll take this out. It's just order of magnitude. The delta m squared is 2.5 10 to the minus 3 in eV square. The distance, we'll just put L in kilometer. Let's make 10,000 kilometers. So the radius of the Earth is 6,000. 10,000 is actually like from two almost opposite corners of the planet. And now we put the energy in GeV, and this should be about 1. So if you look here, for this to be 1, your energy, what is this? 10, 25. So your energy needs to be below 25 GeV, okay? If you lower the energy, you can lower L. Being a little bit more realistic, 10,000 kilometers is actually pretty far. And experimentally, it's very, very hard to create an accelerator where you shoot neutrinos down, right? Unfortunately, the Earth is round. So what you want to do is to shoot neutrinos a little bit off the horizon. So you might actually want 1,000 kilometers-ish, not 10,000, which will put this energy more at the few GeV ballpark. So essentially, doing a back of the envelope, 5 GeV is a good number. You don't go above 5. If you go above 5, you start not seeing oscillations anymore, or you need to build a detector in the other side of the planet too hard. If you go below 0.3, you don't produce muons enough. You lose like a golden channel, which is nu mu to nu mu disappearance. So that's fine. What's the problem with that? The problem of that is that now, when your neutrinos interact, they interact with a nucleus, and this is just a sketchy diagram. It's not supposed to be a Feynman diagram. You have an argon nucleus. The neutrino probes the nucleus and may hit like a proton inside the nucleus, right? Let's make it a neutron, which becomes a proton. Why is this hard? If you are at very, very low energies, your nucleus, you see the nucleus as a big blob. You don't distinguish the stuff inside. That makes life a little bit easier. This is too high of an energy to do that. If you go like to the TeV scale, like LHC, you don't see the nucleus itself. You see PDFs, you see quarks. So I'm not going to say it's easy, but it's, well, up to some extent, it's perturbative physics. You at least have a way of dealing with the theory uncertainties. At these energies, this is precisely the bad energy range for understanding what's going on here. There's a lot that can happen here. And I'll just go through a little bit of that so that you can understand how hard it is to predict these cross-sections with a good accuracy. So the typical binding energy of a nucleus is of order 30 MeV-ish. The mass of a pion is of order 140 MeV. And the mass of a proton is about 1 GeV. So you see here, there's no very, very clear separation of scales. Pions are what mediates interaction between nucleons. Binding energy is what tells you how you can see the entire nucleus. And if you start to get to the mass of the proton, you actually start ripping the proton apart. So the separation of scales here is horrible. There's a lot of non-perturbative physics that happens on this kind of interactions. And it's hard even to know, even to get like an approximation parameter. For example, if you're doing QED, you calculate a cross-section. Your cross-section typically goes like alpha or maybe alpha square. That's a small parameter. If you do a loop calculation, it will go like alpha to the 4 or something. That's great. You know that the loop is much smaller than the tree level. This doesn't really work like that. There is a lot of stuff where your approximation parameters, your small parameter is more like 0.4. That's not that small. And there is stuff that you don't even have an approximation parameter. So for example, let me just list you some of these problems. So the first thing you need to say, you need to be able to understand here, is the nuclear configuration. Nuclear configuration. So what is that? If I'm hitting a nucleon inside the nucleus, you gotta tell me what's the speed that is traveling. Like the nucleus is not a static sum of nucleons. It is a bound state of nucleons at some temperature. So there are several ways people can model that with what people call global Fermi gas. That's bad, don't use that. Local Fermi gas, spectral functions, and so on and so forth. These are all like different ways to model the initial state of a nucleus. Many of these things, they do not have super well-defined error bars, okay? It's not trying to blame people, but it's just hard to estimate an error bar for that. It's a hard business. So the second thing you need to know, so if you do that, you know like if this guy was moving that way or that way with some momentum. The second thing is actually this interaction vertex. You know, when a neutrino interacts with an electron via W, you can just take your Lagrangian, look at the coupling, boom, you know it. If it interacts with a proton, the proton has structure. So you can't really like extract that from first principles. So what you do is that you parameterize the nucleon form factor. So the form factor is just a fancy name to say there are many ways I can couple to a proton in a Lorentz invariant, Lorentz covariant way. I write all possible ways, and in front of every structure, you say there is a function here which I need to define, I need to measure. I can use some physics arguments to like extract part of what these functions are, but most of them, you gotta measure them. That also has uncertainties. There is what some people call the, oh, this is even a fancier word, intranuclear cascade. I don't know if you realize, but as we go into cross sections, the density of weird names grows exponentially. And I don't know exactly why that is. Maybe it's just the fact that lots of these things came from nuclear physics, and most of us are not trained on nuclear physics, so the names sound very weird to us. Most of these things are actually simple concepts, so do not get thrown away by this horrible name, right? The internuclear cascade essentially tells you, if I hit a proton inside a nucleus, what comes out? Tell me exactly, like, if one proton is hit with a 1 GeV of kinetic energy inside the nucleus, give me what comes out of the nucleus. The intranuclear cascade is how do you like describe that? One possibility is like a billiard ball-like. So imagine that I have a bunch of stuff here, nucleons. I push a proton. As the proton exits the nucleus, I know the configuration from some of this stuff, like the spectral function configuration. And I can calculate what's the probability that this proton interacts before exiting the nucleus. If it hits something else, just billiard ball it. Now there is a neutron and a proton trying to come out. And they will propagate, and maybe they'll hit something, and now there's something else coming out. This sounds easy. It's not that easy. But more importantly, there's a lot of effects here which are not easy to model. It's not like you have an expansion. You gotta model this with some ideas that you don't fully control how much you're losing with your modeling. Then there is a few more stuff, like you need to account for Pauli blocking. So that is, if you remember, nucleons are fermions. Nucleons are fermions, and if you hit a nucleon and it wants to be kicked out with an energy that is very low, these energy levels may already be full in the nucleus, right? Because this is like a bunch of it's a fermion gas-ish. So you need to account for that, for the fermion character of the nucleons, to make sure that you're calculating the right rate of scattering. And there is stuff besides Pauli blocking. What was I going to say? I forgot. Besides Pauli blocking, what do we have besides Pauli blocking? Oh, binding energy. Yes. Because even if you kick a proton, but this proton is very slow, it shouldn't exit the nucleus, right? You need some minimum energy for it to exit the nucleus. After all that, then you can say things like, my 1 GeV neutrino hit the nucleus, and now I got coming out a muon, a neutron with a certain energy, and a proton with a certain energy. And then these things need to be compared with what you measure experimentally. So just for me to finish, this is like the main challenge of beam neutrinos. It was not a big of a challenge before because the experiments did not have enough precision to be able to distinguish all that. But now with the future Dune experiments especially, we will be able to reconstruct every single charged particle in your event up to very low energies. So you gotta know what's coming out. This is a big deal. We need people working on that. If you have a knack for nuclear physics and generators, be my guest. But it's challenging. So I'm probably out of time. Questions?
Thank you. So a quick question. Otherwise, we continue at 5 with the general questions.
Modelo de partícula, antipartícula, de Fermi-C. Sim, sim. So there are parts of this cross sections which is it cannot be just described as you hitting a proton, for example. You can hit a correlated pair of proton and neutron, for example, which is very bound together. That is what some people call erroneously 2p2h, two particle, two hole. Nobody should use that. The right way to call them is by meson exchange currents. Again, another horrible name. And there is more stuff that could happen. You could like excite the nucleon. Instead, to say a proton could become a delta resonance, which is one of the horrible baryonic resonance which decay in a specific way and so on and so forth. So there is a lot going on there. But yes, the two particle, two hole stuff is directly related to that.
Thank you, Pedro. We will continue in the afternoon with the question. If you have question, write in your